You can open the previous database or make a new one. I'll create a new database. I'll call it HyperSizer V7 wing box. When the database opens, essentially the materials are provided, and if you expand the isotropic as an example, aluminum, you can see all of the aluminum alloys that are shipped with the database. What we want to do next is to import from the Airframe database template. Go to the Advanced button, the Custom Analysis selections, and the database defaults. Close and close. And so now the wing box is set up with our preferred aerospace analysis methods. Create an FEA project. We'll name it Wing Box Advanced Sizing C131 to indicate that there are 131 sizing components in the upper surface of this wing. We'll use the MSC Nastran solver. We'll locate an existing model under the FEA folder, Nastran Technique 1, C131. Note that the software identified the associated FEA output file, the binary OP2. We'll import the model. And you can see 4 load cases identified here. If we go back to the setup, we can open this model. We'll open it with Notepad and see the 4 subcases here with the subtitles. For example, subcase 300 is a 2G taxi bump, and if we take this guy away and cancel, we can see here 300 is the 2G taxi bump. At any time you can choose to have these subcases included or not included in the sizing optimization. For now, let's just leave the first subcase turned on, hit save. Let's click the FEM viewer, take a peek at the model. We can mirror it about the y-axis so we have a better feel for the structure. Now, unlike the previous tutorial where we had 27 components, here we have components defined in the chordwise direction as well as in the spanwise direction. Let's go to data, let's look at the loads, and let's turn off the beams so that we can have the automatic color scale adjusted to the peak element load of just shell elements. We can also use this icon here to change the amount of significant figures, and we can right click to look at the values smoothed. So this is the load case 1 where the compressive load peaking around 13,400 pounds per inch of compression, and load case 2, which is the upgust 5,300 pounds per inch in tension, load case 3, which is the 2G taxi bump, and then lastly the 2-point brake roll, load case 4. So let's take the graphics away. We have the setup form. We'll click the sizing form button to pull up the sizing form. And what we'll do is follow the process indicated with the orange highlight. The first step being to create the assembly. The model is shown in the last way it was viewed Let's do not mirror it. Let's turn off the data, have a cleaner legend here. And what we would want to do next is to use the dialog to assign which components comprise the first assembly. Now the first assembly is going to be the upper surface, and we want this surface to be the same surface area as used in the previous tutorial example with the C27 model. And you could go interactively and pick the different components, but since we're familiar with the numbering scheme, we'll simply just type in the component range or the property ID P-shell range of interest, and we can update the pick, we can turn on the icons, and you can see indeed this is the same area as used in the previous example. So we'll say that's good. We'll not create another one, and we'll apply, and you can see the components on the assembly with a full model in this fashion. And you can turn on the marker here, maybe turn off the mesh, and this is the area that will be sized. Let's turn on the property IDs directly on the finite element model, and as I move my cursor over the legend, you can see the image updating accordingly. Let's take this away. Let's go to the sizing form, and let's select the next step, which is the material mode. We want to go with composite, and we're going to do a quick sizing. So we then have to select the concept, uniaxial stiffened family, I-bonded, apply this to all components in the assembly, OK. And you can see the image here with the labels defined, and the numerical value will be filled out here. Let's right click and select material. We're going to use a composite tape, a damage tolerant allowable material. We will select this one for the skin. Another way we can do the same thing is go to the laminate stiffener tab, select tape, select that material, and we're pretty much ready to perform the quick sizing. But let me mention one thing, and that is it's necessary to make an adjustment to the Y span of the buckling length for these components. Let's plot those values on the model. So we will go to use that icon, show buckling lengths, and we will turn off the edges. So you can see here they are correctly identified in the rib to rib direction, but in the spar to spar direction, they're not the way we would want them. The software defines the width of the panel span as the width of the defined sizing component. We need to manually overwrite these values for now. The actual dimension in the chordwise direction is not significant for our purposes, so let's just set all of them to the average value of 60. So when I go back to the buckling span here, I'll just set all of the value to 60, hit save, and then right click and apply all to the assembly called upper surface. Now when I go back to my graphics, you can see that the spans have been updated accordingly. And now you can see all of the values now have the 60. We'll turn that off, and we'll go back to the sizing form, to the dimension tab, and perform the quick sizing. The quick sizing results are complete now, and we will be able to see those. The first thing we can do is take a look at the margins of safety and see that we have positive margins everywhere. Next, let's plot the unit weight of the panels, And as you can see here, the red is the heavier and the blue and purplish color representing the lighter weight panels. This is not surprising. It follows the load gradient we saw earlier from the internal load. Let's plot next the laminate skin ply percentages of 45, the darker being more 45s. We have upwards 60% 45s in some areas of the wing skin, and I would say an average around 40% 45s, and dropping all the way down to some areas of 25% 45s. This kind of follows the pattern we saw with the shear. Let's plot next the percent of 90-degree plies. The range goes from 10 to about 17%, with an average of around 12%. Of course, all of the panels are meeting the required 10% 90-degree plying. And this is, I brought this to your attention because in a trade study we'll perform next, you'll notice how this value is changing. And next, let's plot the thickness of the skin laminate. Now we will be plotting the distribution of 0 degrees. And you can see here some of the skin ranges to 60% 0, with an average around, say, 50 to 45, and the green pattern going all the way from root to tip of the wing. Okay, let's plot another piece of data. Let's look at the output variable spacing and plot its component result. We can see here that in this area of high load, it's close to 12.5 inches, going down to about an average of 7 inches for most of the wing skin, and then at the outboard section, it's closer to 2-3 inches. Obviously, it's not possible to fabricate a stiffened panel with this varying stiffener pitch. And so we're going to go next to the design criteria form, where we can go into the tooling and we can specify value. So we're going to require that all of the stiffened panels have a 7-inch stiffener spacing from root to tip. And we can say apply and OK. Now before I do that, let me go to the summary form and show that for this assembly here, it weighs 434 pounds, the upper surface. That's where each stiffener is allowed to optimize freely based on its load magnitude. And so now that we had changed it to 7, we will do another optimization, quick sizing optimization. And we see now the weight went to 469 pounds, which is very close to an 8% weight increase over what it was before. Going back now to the graphic, we see that all of the panels are 7 inches for the spacing variable. And if I go back to looking at the percent of zeros, I can see that down here in the tip, whereas before we had a lot of 0%, we do not anymore. And in its place, we can plot the 90-degree ply and see that we're upwards close to 45% of some of these panels, and the amount of 90-degree ply, and that is in the direction perpendicular to the stiffener. Of course, the value in that is it enhances the local skin buckling stability. And these areas want to have a tighter span, but forcing it to have 7 inches causes the local buckling to be the critical failure mode, and hence the need for more 90s to prevent that mode shape. So in the area here that has the high 90s, we can click in the legend and go directly to that component in the sizing form. And we can see here that the percent of 0 is 12. There's 44% 45 and 44% 90s. for a total of 16 plies, or we have 20, 745, and 790 plies in that skin. We can view cross section and see its aspect ratio, and so the distance basically would be from there to there with one stiffener. So going from the lightly loaded panel controlled by local buckling and having a high percent of 90s and 45s, let's go to the opposite end of the wing, which is highly loaded and controlled by strength. We will use the graphics to quickly identify an appropriate panel. Now displayed here is the percent zeros across the wing surface. Let's pick this panel here in the higher part of the range, 1063. When we go back to the sizing form, we can see that it is automatically brought up, made active, where we can see the 60% of zero for the skin, 58% zeros for the web and foot, and 70% zeros for the cap. Most likely the true optimum for this component would have a higher percent of 0 degree plies and these panel objects. They are being constrained to the max percent values based on design criteria. Let's go to the ply angles criteria, and here we can see that for tape the max percent allowed for those objects is 60%, though we are allowing 70% in the cap. Note also that the minimum of 10% is being used for 0 and 10% for the 90s. The design criteria ply angle percents are considered limits to never exceed for any component in the project, as they are most likely imposed by your company's materials and processing department. As such, they apply to all of the different methods HyperSizer uses to optimize laminates. Going back to that highly loaded component, within these min and max percents for all the different angles, the quick sizing optimizer selects the optimum ply counts shown here for each angle. The challenge now is to convert these ply counts into actual laminates that also have their additional design criteria that must be followed, like maintaining symmetry and balance. The conversion of ply counts to laminates happens during the detailed sizing mode. In this mode, the layup rules become relevant. These rules control the generation of the laminates. These rules, shown in the top right of the form, are from aerospace composite design and stress manuals. Even though it's a small part of the form, they include almost every guideline used in industry. The rest of the form provides a way to specify how the laminates are to be stacked with full body plies for the assembly. As such, they are meant for fabricating more producible parts. The sublaminate is another method used to reduce cost by purchasing layers of materials as a unit that speeds layup on the tool. So the key is maintaining optimal ply counts in the objects of the stiffener while also producing a laminate that satisfies simultaneously these layup rules with another set called fabrication criteria. We'll go to that next. And we do that by going to the set variables icon and clicking here. Using the figure to the left for definition of terms such as base laminate, cap charge, ply pack, foot charge, plank, and then looking to the top right of the form, you can control how the optimization will produce stiffener laminates comprised of these sublaminates. These options relate to how your company will fabricate the stiffener. Since it involves tooling which is directly related to manufacturing cost, The decision of which option to use is subject to a specific manufacturing approach. If your company has one particular approach, then put a single check in a box. However, the software will allow you to put a check into as many boxes as you would like to be considered. The circle radio button indicates your preferred selection. With all else being the same, such as unit weight, the optimizer will choose this option as it generates sublaminates per panel segment. The variables defined on the bottom left are used with the table entry on the bottom right. Of particular interest is RSA, the ratio of stiffener area divided by the total panel area. For discrete source damage containment, designers usually stay within the bounds of 40 to 60%. A lower value tends to make the skins thicker and the stiffeners spaced further apart, requiring less overall panel stringers in your structure. The other R ratios and their settings are based on similar industry best practices. They also account for repair rules and help the sizing optimization to more directly define panels that will satisfy these. You can specify repair rules in another form. So let's cancel out of this and go to the Design Criteria button and then hitting the Repair icon. The repair rules are noted with the C ratio, and they also have a minimum and maximum value as well. And you can see here some of the equations used for those. Let's take this away now, and we would like to transition from the quick sizing results, basically ply counts, to detailed sizing with the laminates. To start this process, we begin by clicking the Set Variables button on the ribbon. We will do this with the assembly. The Set Variables form establishes the proper min and max bounds per variable. The function of this form was described in the initial sizing video. Note though, there are 4 presets for your convenience. You can also overwrite any of these values manually. Let's go back to the initial value and hit the Set Variables. What it's doing at this point is generating candidate laminates for the skin and for the stiffener per each panel bay. And of course it's developing the min and max bounds to use for all the cross-sectional variables. Together, those variations or combinations produce what we call candidate designs. In this case, there'll be somewhere in the order of 1,200 candidate designs produced. Now that it's done, let's hit OK. And we can see here for this 1063 component, there were 20 discrete laminates generated and 7 discrete laminates generated for the stiffener. We have the stiffener spacing set at 7 inches. So even though we previously in the form said to vary that value, the fact that from a tooling constraint we set this explicitly to 7 reduces the number of candidates from the 1,200 to the 400. You could, if you so choose, to overwrite the entries in this table that were put there from the Set Variables form. For instance, I could take the number of steps there for height and make that value 5. And see the number updated to 700. Again, if I make that 1260. Likewise, if we wanted to, we could add additional discrete laminates to the candidate list below. But let's keep it the way it originally was set up. And we will next go to the detailed sizing, which you can also see from here, and click it and get this optimization process started for the entire upper wing skin panel. It's complete now, and we could go to looking at the cross section that was optimized for that 1063 and take our cursor, click it, and then use the wheel and zoom in or shift and put the image in this fashion. You can see here that for the bottom, for the cap, we also have these cap charges. So if you look in the description or the unique ply ID or the ply angle, you can see the information here updating. And so this happens to be unique ply 24, cap charge ply number 9. Whereas if I go over here, this is unique ply 33. Is the web left base laminate local ply number 6, angle 45. Let me point out, zooming back onto the skin itself, that we have a 45, a 90, a minus 45, and another 90 on both the OML and IML of the skin. The reason the laminate has this is because on the layup rule we explicitly define these full assembly plies. Also note that at the midplane we have a 90-degree ply. So let's take this away and let's go back to the design criteria and look at the layup rules closer this time. And you can see again the 4590 minus 4590 there for the first plies. The last plies are the same 4 but symmetric with the first ply, and the midplane plies actually are a 090. Let's go to the laminate skin and the sequencing function and make this full screen. And what we want to do is to do a quick sizing on the results we have already. The message is telling us no transitions are defined for this variable. Would you like to create them? Say yes. And 135 were generated automatically. You can see those in the graphics. And these transitions essentially are determining the contiguous neighbors between each of the different laminates. After doing that, then we can actually sequence. And it's analytically it's performed all the sequencing calcs, and now it's displaying those for you. We have about 245 individual global plies, so it's going to make it very challenging to see the information in this kind of manner. And so, falling back on the original tutorial called initial sizing, we kind of gave a description of how this software form operates. Let's go ahead and do a full sequencing, but we'll keep the slider bar to the left to minimize weight, hit sequence, and it will go off and perform its sequencing, as you see here with the number of passes. And we see here that the number of drops have reduced to 1,600 and global plies to 203. Max plies not interleaved improved from 13, now they're 9. We can perform other functions as well. One is to actually shuffle to the OML. Before we do that, let's just take a quick look at the built up global plies. And we can see them here and rotate it that way. And so we have the full body plies on the whole tool, and then you can start seeing the pattern, the way which the composite would actually be fabricated, the layup process of the individual layers. And you can go through this software legend to see such data. Let's take that away, and let's go ahead and shuffle to the IML OML. And in this scenario, you should see a greatly improved solution. And it's done, and you can see the global plies 91, drops and adds 570, and the plies not interleaved is now 6. Let's plot again, this time in the exploded view. And now we can see the solution in this manner. We can go right click on the legend, open the configuration dialog box, and separate these plies a lot so we can get a much better understanding of how it actually would be stacked up. And you can see it in this manner. And again, we can stack them up like this on top of each other to kind of see what's happening. You may notice that if you stop right there and see kind of a non-rectangular type view of the way the pattern is being developed here, so like a jigsaw puzzle, there's one additional feature that you may want to do, and which is to make rectangular. The wind blade manufacturing industry likes this feature, and the purpose of which is to, without much of a weight impact, to try to take away the zigzag pattern in the layups and make them more square. And let's go over here now, and one more time let's look at the exploded view, and we can kind of go down this way, maybe turn it a little bit this way, and see how they're stacking up. And you can see that in general they are more rectangular, not all of them, but it's not as bad as it was before. And of course the purpose was to try to minimize weight impacts. Another useful way to see the information is to hit the Shift Control Alt key pattern, then left finger of the mouse, and start drawing a line across the surface, sort of like a snap line. And once this is done, then you can zoom in on it at some location here, and you can see the actual layers more explicitly here. And these are 90s that are dropping, and here we can see some zeros that are being added. And you can go down and see some 90s being added there, and then of course the 90s drop, and you're seeing some 45s being added. And continue on in this manner till you get closer to the root, which you can zoom in this fashion and see the complete laminate definition at that point. I'm going to take this away, do this one more time. So really, with the Shift Control Alt snap line, you can draw it in any kind of arbitrary manner like that and see what's happening. So we can again zoom in right here, can zoom in at that location, at this location here, and so forth.